Hello, welcome to this video. Today we're going to do a probably overkill proof of Thale's theorem, which states if DE is parallel to BC in a triangle ABC, then BC over DE is AB over AD. Seemingly innocent and honestly pretty obvious proof. Honestly pretty obvious theorem, because if you scale this up by something, then this will obviously scale up by the same amount. But let's begin. Prove it in a probably very non-efficient way, and you'll see the complexity of mathematics. So I'm going to first of all make a couple notations. If BC over DE is X, I'm going to write AB over AD is Rx. And the goal is to prove Rx is just equal to X. So let's begin. So first things first, we'll show R2 is 2. So if BC is twice the length of DE, we'll show AB is twice the length of AD. So let's draw this. So now, let's pick the midpoint of BC and we'll call it F. And let's look at the lines DF and EF. Let's see. We know DE is parallel to FC, but we also know DE is equal to 1/2 of BC, which is exactly FC. So these lines are also equal length, meaning that we have here a parallelogram, meaning that DF is parallel to EC and equal to EC. Similarly, DE is equal to BF and parallel to BF, so EF and BD are parallel and equal in length. Now let's look at ADFE. We know DF is parallel to EC, meaning that it is parallel to AE. And we know EF is parallel to BD, meaning that it's parallel to AD, meaning that ADFE is another parallelogram, meaning that AD is equal in length to EF, and AE is equal in length to DF. Meaning that all in all, AD is equal to BD. So AD plus BD, which is AB, is equal to twice AD. So AB over AD is 2. And we proved this statement. So R2 is equal to 2. Now let's show for all n that are natural numbers, Rn is equal to n. So we're going to do this with induction. N is equal to 2 is our base case, which we already proved. Now let's begin. So assume we have our triangle. This is A. This is DE. This is BC. And we know BC over DE is n plus 1. We need to show AB over AD is n plus 1. So let's pick points F on AB and G on AC such that FG over DE is equal to 2. So FG is twice the length of DE. And now, let's look at the midpoint of FG. I'll call it H. Let's pass the line DH. We proved DEGH is a parallelogram, so DH is parallel to EG, meaning that if I call this K, DK is parallel to EC, and we know it's given that DE is parallel to BC and therefore KC. So this is another parallelogram, meaning that KC is equal to DE. Now, by how we defined H as the middle of FG, we know HF is equal to DE. And now we defined FG to also be parallel to DE and BC, meaning that FH is also parallel to BK. Now let's see, what is BK over FH? Well, BK is BC minus KC, and FH we know is equal to DE. BC over DE, it's given that it's n plus 1. KC over DE, we know is 1 because they're equal in length, so this is n. And by our induction hypothesis, by our assumption, we now get that BD divided by DF is equal to n. And we know by what we proved that R2 is equal to 2, DF is equal to AD, so BD over AD is n, but if we add 1, we get AB over AD is n plus 1. And we proved by induction that this statement is true. Alright. Now let's clear the board and continue from here. Alright, let's prove. So we proved for 2, and from there on to natural numbers. Now let's prove it for all rational numbers. So suppose here BC divided by DE is equal to m over n. For m and n being natural numbers, we need to show that AB over AD is m over n. So I drew another B prime C prime, and I drew them so that B prime C prime divided by DE is equal to n. And because of our given, we know B prime C prime divided by BC is n. And of course, all of these are parallel. And because of what we proved for natural numbers, we know that AB prime divided by AD is equal to n from this, and AB prime divided by AB is equal to n from this. Now it's a case of this divided by this. AD stays at the bottom. 1 divided AB goes to the top. AB prime cancels out, and we have ourselves AB over AD is equal to m over n, just like we wanted. So now we prove it for rational numbers. Now let's prove an inequality that will help us prove it for all real numbers. So for x smaller than y, we will show our x is smaller than our y. So let's see. Suppose we have this triangle. We have ABC, DE, FG. Now x is smaller than y, so we know BC over FG is x, because FG is longer than DE, and BC over DE is y. DE is shorter, DE is smaller than FG, so 1 over it, y is bigger than x. But now let's look at what is our x. We know AB over AF is equal to RX, and AB over AD is equal to RY. Now, let's see. We know, obviously, AD is smaller than DF. So 1 over AD bigger than DF, 1 over DF. So after multiplying by AB, we get exactly RY is bigger than RX, just like we wanted. Alright, now we proved this. Now let's show that it works for all real numbers. So suppose now we have a real number x. We want to show Rx is equal to x. So because of the density of the rationals in the real numbers, we know there's a series of rational numbers that approaches x from below. So Q1n is smaller than x and tends towards x. Similarly, there is a series Q2n that is bigger than x and also approaches x. Now, because of what we proved, we know Rx is smaller than Rq2n, but we know that's just Q2n. And Rx is bigger than Rq1n, but that is just Q1n. And now let's let n tend towards infinity. And as n tends towards infinity, this tends to x, this tends to x, and by sandwich theorem, Rx also tends to x. But because Rx is a constant, so the series Rx is just the same number over and over, it approaches itself. So Rx approaches x and Rx, meaning that Rx has to equal x for all x that are real, obviously, numbers that are obviously bigger than 1. Which proves Thale's theorem in the most overkill way possible. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.